Okay. Good afternoon, I'm Boqun from Huawei. Today I'd like to talk about recursive, read deadlocks, and where to find them. This topic is a bit informative and time's limited, so we'll first go through the background and some of the information. I would like to assume that you are all aware of it, and if you have questions, then you're welcome to approach me privately after this session. And then today I would like to talk about several topics. The Lockdep, and where to find deadlock and how to assess it, and what I do based on Lockdep, and how can we detect Lockdep. How can we detect deadlock? First, pretty simple deadlock. Let's skip this part, and basically if it's involved in it's relevant with deadlock and self-deadlock and ABBA deadlock. To the lower right corner, what we see here, I'm gonna assume that you understand it, and both A and B are in the locked up status, unable to proceed. ABBA can be expanded into a 3 deadlock sequence, and also there are some deadlocks relevant with interrupts. So basically we can assume that's an expansion or scaling of ABBA and self-deadlock, and if we're trying to solve a deadlock, then no matter the code, if there is deadlock, then we will find a specific combination of codes, and the interrupt will increase the possibility of deadlock code occurrence. Well, if you have a IOV enabled context and you drop the ABBA deadlock, then there is a deadlock. P0 RQ is enabled, and there's a span lock A, and there's a lock handler, then they will handle lock B, but lock B is locked, and in turn they will spin lock A, and then there is a deadlock, and it will be expanded to a 3 deadlock chain. Lockdep, what is it? Lockdep is a deadlock assessing tools, and it's a self-equipped tools in the kernel, and it's developed around 2000, and it tried to minimize the occurrence of code in deadlock, and they will they will classify different categories of deadlocks, and there is a concept of lock dependency. To the right, you can see P0. If there is a spin lock A and spin lock B, then we assume that A to B there is a lock dependence. Based on the dependence, then we will have a dependency graph. It's pretty simple, pretty straightforward. We will see the lock dependency graph. Is there any ring layout? And if there is a ring in the lock dependency graph, and that will be ABBA deadlock, then this is the code that is likely to appear. The lock dependency graph is going to have this code. So this case is a typical deadlock case. And here I won't go into great details. If you're interested, then you're more than welcome to do more research on the condition of deadlock. And obviously, in all our cases, it's all spin lock, and in kernel there are some other cases. The Lockdep are dealing with it like the following. Well, first let's focus on Lockdep. So two rwlock, one is recursive rwlock, unfair rwlock, and the yellow arrow is where the time progresses. W1, writer 1 in red, that means they won't get the lock. And next we have R2, reader 2, and they get the lock. And if it's like this, then it's a non-common rwlock. If we have writers keep coming, then W1 will not get the lock. It's unfair, and the writer will be very hungry, and it's not very good. And so all the rwlock is fair rwlock. So these are two cases. So the yellow arrow is where the time progress forward, and R2 won't get the lock, and W1 will have high priority on getting the lock. If it's like what's to the right, if we don't have the writer, then R2 can get the lock. So it's a rwlock. It's different from the previous deadlock. When the reader get the lock, and if there's any writer, there's no other writer, then the rest of the reader can also get the lock. So there's the difference. So we can summarize in this graph saying that the recursive rwlock or deadlock, they will have multiple readers, and they will allow recursive reader to have a critical zone, and one reader will not block the other readers. And for non-recursive, it's rwlock, and also they will allow multiple readers, but they will not allow recursive CS. It's called non-recursive, obviously, and the non-recursive reader will block other reader, and they will have a signal. This one. Here you can see the R1 sometimes are now blocking R2, but sometimes R1, when they get the lock, will block R2. When R1 not getting the lock, R2 will not get the lock as well. So R1 will block R2 with the non-relevant writers. So that's what we called one writer can block other writers. One reader can block other readers. So this is the condition of blocking, differentiating different cases, different scenarios. So spin lock can be considered as the scenarios the only writers exist. So if we view this graphic horizontally, the recursive reader, they will not block any other readers, whether it's recursive or not. And a recursive reader will not block other readers because it's recursive, and it will block writers. And the non-recursive, no matter it's reader or writer, well, first, from recursive aspects, they will not allow CS zone, and the writer is non-recursive lock. The non-recursive, no matter it's reader or writer, they would block other reader and also other writer. This is the block condition. And starting from here, this is what we called, if we say this rwlock is a non-recursive rwlock, then if we're not focusing on P2 but also P0, P1, then it's like the previous example. But if we want to trigger this deadlock, then we need P2. If there's no P2, P1, when they get the B, then they can proceed to A. If you're assessing, detecting any deadlock, you will have to go through all, you have to rule out all the possibilities of deadlock. And if the codes have P0 and P1, then there's still the possibility of not being a deadlock. And rwlock is a recursive lock, then obviously this is not a deadlock. A recursive lock will not be blocked by another reader, and if they have a P2, then P1 will still have to be a spin. This can still get the lock, so this is non-deadlock, and the Lockdep graph can be changed to this, and A to B and B to A. There's a ring, and it's not a deadlock. And this is deadlock itself, and the writer will be blocked by reader. The red lock will be blocked by P0. And if it's a ring layout, then we can see that here B to A is a WW. This is not the initial lock. B is a write lock, and A is also a write lock, and P1. That's the case. So they have the same struct, but the categories is different. One is deadlock and the other is not. So for the same struct, they might have different categories of lock. Sometimes it is determined as a deadlock, sometimes it is not. And well, if it's a non-recursive read lock, then if it's in the RQ context, it's a recursive deadlock. They have to guarantee that the handler can get the lock and exceed ASAP, and it's a famous deadlock example. It's pretty special. And this is deadlock example. This is read lock. This is a bit different. To the upper right corner, it's a recursive deadlock, the green bit, and the other read lock is non-recursive. This is a deadlock, and deadlock A. If P0 get to B and P1 will not get the B, because if we have a non-relevant readers, then the blocking condition is that the P1 is when it's getting the B, it's a functional reader lock. If they have writers there, then the writers will first get the lock, and then the readers will get the lock. So the P1 read lock won't be able to get the lock. It's a ring struct. So later we're gonna touch upon that. Next, this is not a deadlock. We just reverse the sequence. So we can see P0 get A, P1 get B, P0 now wants to get the B. It is possible, it is accessible, The lock is a recursive rwlock, and they have a P2 writer, but still they can get the lock. So this is not a deadlock itself. So Lockdep, if you're just assessing the ring, then we'll be missing some of the conditions of the deadlock. We need to make several changes. First, we have to make sure the existing deadlock is working, Lockdep is working, and also we have to handle the queue added lock, and we have to consider the false positive situation. And if we have a false positive detection tool, then people are not trusting the tool. You can miss some of the deadlock, it's okay, but if you report a false positive result, and you might lose the trust from the clients, you have to guarantee the tool is trustworthy. The Lockdep, we must rule out the possibility of false positive. So this is very simply about how can we detect recursive rewrite lock, and we classify it as follows. First, we consider that we have three categories of rewrite lock. First, R reader, recursive reader, and non-recursive reader, and writer. In one dependency, we're gonna have 9 combinations, 3 times 3. So this is a direct sorting up according to the Lockdep conditions. 4 categories: 1, shared locks, reader locks, recursive or not, and exclusive locks, writer lock or plain spin locks, and recursive readers, and non-recursive readers and writers. It's represented by letters SE and SERN, and recursive reader will be blocked by writers. Non-recursive, no matter reader or writer locks, will be possibly blocked by other readers and other writers. So if we summarized it, we got the following graphics. R will be blocked by S, and the others on the other occasion they will be blocked. S means share, E means exclusive, R means recursive and non-recursive, N means non-recursive. So rwlock, the dependency, we have 4 categories in this regard. So why? First, SRN, EN, ER. Based on previous conditions and definitions, we can easily understand that. And I am saying that for the headed dependency, we only need to determine whether it's shared or exclusive. For the tail, we have to determine whether it's recursive and non-recursive. So we will determine the block on this. When we consider lock dependency, we are actually focusing on, first, if we're considering the dependency from A to B, then A will be a lock. What are the conditions it will block, and what other conditions they will be blocked? And B, if we say B can be blocked by the B in BC, and then we can scale up and for the codes in the lower right corner, we can come up with this graphic. From P0 we have a lock dependency SW, sorry, my mistake. It should be SN A to B dependency and B to A EN dependency. And we have to define the two dependencies. One is strong dependency. We have to see how can we expand the lock's dependency guarantee it is a deadlock all the way, and how can we search in the lock dependency graph and guarantee that its head and tail have a strong relations, very strong dependency. See whether we can discover the ring or not, or if we can expand it, if we can scale up, then the dependency from A to B and B to C, if it's meeting the following conditions, that means it's a strong dependency. And if it's only the last condition,
from A to B, there's from regardless what A is, and B is a recursive lock, and from B to C, B is a chain lock. So how can the dependency be transferred? I mean, only in the latter case is not a strong dependency. All the other ones, they are strong dependencies, and we can expand this. So I will introduce why we can omit this one. Because if this kind of situation happens, the B is a recursive reader. Yes, from A to B, the B is a recursive reader, but from B to C, this is a shared reader. And let's look back on the previous ones. The recursive reader cannot be blocked by the non-recursive reader. So there's not a strong dependency here. If you can translate it into codes, it means that P1 first chooses A, and P2 chooses B. But he can still choose the B from A to B. Yeah, you can think about it. Because the other situations, there will be the occurrence of blocking. So this is the strong dependency we have. We think it is can transfer the relationship of the locks. So the deadlock condition, it means that the strong dependency chain forms a circle. And the latter example, it shows the code for the right one. Yeah, it has the deadlock, and because it doesn't contain the R at all. And we can prove that it is also a deadlock. Yeah, P1 get A, and P1 get B, and P2 get C. And the system cannot continue. So suppose this deadlock is a non-recursive. The reader is a non-recursive one. And I have also proved it. It's, yes, we want to prove that there's a kind of a circle, a loop. That based on this definition, we establish a dependency graph. If there's a kind of a loop happening, so it equates to the deadlock possibility. But it doesn't mean that the deadlock is definitely going to happen, because you only need a very special condition to make it happen, to make the deadlock get triggered. But for us, we don't allow this possibility of deadlock occur, because if that happens, then the system will get stuck anytime. Yes, we don't want the deadlock possibility. We make it equate to the deadlock possibility. So suppose we have a strong dependency, we can construct an example. in which the deadlock occurs. And for the reverse ones, we can see that the deadlock possibility means that we will have this condition for circular weight. For the circular weight, we can build a loop gradually. So there must be a strong dependency circle. And this is for the algorithm, and this is for implementation. We change the Lockdep codes and also BMS search codes so as to make it to implement the strong dependency. And we have done some tests on it. The code is shown in the below. Yeah, you can check it. There is one good point is that when the Lockdep just appears, it has its own deadlock test. It's called RQ Reader Recursion 1. Yeah. After I have added the algorithm, it is run very well. It proves that, yeah, my implementation algorithm is consistent with the previous thoughts. Yeah, today my topic is a bit complex and abstract, but I hope that there's 2 points I want to make. First, how can we expand the log dependency relationship? We use the block condition, the weight condition. So suppose I have 2 log dependencies. Yeah, it's easy to find them. If you can have this in the code, then you can find it. How can we expand the log? It's an issue. And another thing is that the dependency block condition. Yes, one reader can be blocked by another reader. Yes, the other things, they are very not that complicated. I mean, the algorithm you can just go deep dive yourself. So that's my presentation today. Thank you. So any questions? I have a question because I haven't used Lockdep. So is it static or dynamic? Yeah, it's a good question. It's a dynamic trace. Yes, it was built dynamically. It's yes, so that it won't affect the operation performance. So it will, but its algorithm analysis is static. So is it plugged? Yes. So we still need to install it when we are writing it. So can you go to the previous ones about the calculation of its dependency? I don't remember whether it's page 3 or 4. Yes, go backward. Yes. Backwards, if you want to calculate a log dependency, is it done by the decipher machine? So Lockdep, its detection can be performed by the machine. But when it's realized in Linux kernel, it's a dynamic. We use to record what kind of log it gets, and this kind of method is not is static. Go back to the dependency graph. So is it dynamically generated? Yes, in log, it is dynamically generated. So it is. So yes, the Lockdep will classify these logs. It won't focus on the instances of these logs. Instead, it focuses on the structure's logs. It will categorize it into one type. But there's another CPU's log. It's another type. Yeah, it has classified it in advance. And we have this kind of a classification method. So after they have written the code, they have already done the classification, and you just need to run it. Yes. So yeah, that's basically the point. So I want to mention that the Lockdep is more to do with the integration. Yes, different systems use the different locks when you want to integrate them. Then there's some deadlock, unpredictable happening. So when you locked up the information, you actually avoid the deadlock. Actually, the deadlock happens more during the integration process. So it's more like a form of the distributor, right? Because as the dispatcher, the scheduler can just allocate the resources. And yes, we can avoid this issue happening through the code. Thank you. I'd like to ask, you talk that Lockdep should avoid false positive. So any instances that there's a deadlock, but it can't detect it. So yes, for me, yes, we have this deadlock. We cannot not detect the blocked lock. And it will think that it doesn't have a deadlock. Yes, you have realized it on the branch. So are you sure about it? Yes, they want to avoid the false positive. Because they will classify these logs. And depending on the ways to classify this, if you give them to the very a few categories, then, for example, there's a deadlock, the file system. You can regard the file in one file system as a disk, and in this way, if the file system, they will just want to get the log all the time because it thinks it's a deadlock. So that's why we want to classify it, to avoid it being regarded as a deadlock. But in some cases there are some deadlock, and we want to skip it. But I can't think of a very detailed case, a specific case. So, yes, I have a question. So, we have these pages right back. It's like when we are just want to get back of it, it will says wait. It's bounded with wait, but the log condition, we can't capture it. You mean the completion wait? Yes, the structure page. They will write back. It will wait for it to be right back, and to make it to turn to off. You mean the wait in Linux? If you use a spin lock, and you will have to wait for it for the wait to be clear to 0. I'm not sure what you are mentioning. Yes, we have this kind of this progress. In last year, there's a Samsung staff. He can detect there's a deadlock with the condition of wait. That is, when you wait, actually you wait with a lock. But for the lock type, it doesn't take into consideration of this case. So it actually waits with a lock. So this wait has a dependency, and it has done up detection method is very great. But it takes longer time to detect it. If you actually doubt there's kind of problem, you have just to print the patch again. Yes, then you can find the issue. Do you remember the name of the Samsung? He's a Korean student. I don't. His surname is Park, P-A-R-K. And you can search for Lockdep. You can find him. He's very active in this area. Yes, I'm running out of time. So thank you very much.